Good morning, class. Today we are continuing with our lectures and we'll be looking at complexometric titration. We started last week, the last session of lectures we had were on acid-base titration, and today we are moving on to complexometric titration. And this class is divided into different segments. We have the introduction, what complexometric titration is all about, with the example of metal EDTA titration, the types of indicators that we use for this type of titration, EDTA titration techniques, masking and demasking agents, application of this type of titration, and we'll also look at the EDTA titration curve. By introduction, when we talk about complexometric titration, it means that there is a formation of a complex. And this complex we're talking about is a metal ion which is surrounded by molecules or anions. And these complexes are usually formed when a metal ion is combined with an electron donating group or a nucleophile. Look at the example in the equation below. We have copper ion reacting with ammonia, and it forms a complex whereby the ion there, which is your copper ion, is surrounded by 4 molecules of ammonia. So by definition, complexometric titrations are titrations that are based on the formation of complex ions. And it is an analytical method that is used to determine larger number of metals that form soluble salts or slightly dissociated complexes. On the periodic table, almost all metals on the table are able to form complexes with electron donating agents, and these electron donating agents are called ligands. And examples of them are oxygen, nitrogen, or sulfur atoms. If you look at the previous example, the molecule of ammonia has a lone pair of electron on nitrogen. So any compound that has electron donating agents will be able to form complexes with the metal ion. And these metals are electron accepting species, while the ligands are Lewis bases, that is, they are electron pair donors. So the combination of the metal ion and the ligand will give rise to the complex. So what are these ligands? These are complexing agents that bind with the metals to form complexes as seen in the previous slide. And the number of ligands that complexes metals depends on the coordination number of the metal. So the metal has a coordination number of 2, with the number of ligands will be different from a metal that has the coordination number of 4. And looking at ligands generally, there are 2 major categories of ligands. The first class are the monodentate ligands. And when you hear the word mono means 1. It means that these are ligands that bind the metal ion through only 1 atom. And let's go back to the equation we had before. Ammonia has 4 atoms, 1 nitrogen atom and 3 hydrogen atoms. But the mode of formation is through the nitrogen atom that has a lone pair of electrons. So this is the only site ammonia can use to complex with copper. So we can say, as an example of monodentate ligand, that ammonia is a monodentate ligand because it is only forming complex via the site of nitrogen atom in the entire molecule. So that's all about monodentate ligands. And I want you to find other examples of monodentate ligands apart from ammonia. Then we have multidentate ligands. The multidentate ligands are the ligands that attach to the metal ion through more than 1 ligand atom. We have bidentate ligand, we have tridentate, we have hexadentate, depending on the binding site. So an example of bidentate ligand is ethylene diamine, and that is the structure, the molecular formula here. And in this molecule, you find out that the 2 nitrogen atoms have the 2 lone pairs of electrons. So these are the 2 sites through which ethylene diamine can form a complex with a metal ion. So the sites of attachment are the two nitrogen atoms on the two ends of the molecule, meaning that two pairs of electrons will be donated by the two nitrogen atoms. Another multidentate ligand that is very common and popular is ethylene diamine tetraacetic acid, popularly known as EDTA. EDTA is hexadentate because it's going to bind to the metal ion at 6 different sites. We look at the structure of that shortly. So these are the other examples. We've seen ammonia, NH3, tridentate. This is diethylene triamine. And you see here that there are 3 amine groups, and on each amine functional group, you have a lone pair of electron on the nitrogen. So tridentate ligand will form a complex via these 3 sites. And this is the triethylene tetraamine. This is a tetradentate ligand, meaning that there are 4 sites via the complexation of this ligand with the metal ion. So we have 4 amine groups, and these are the 4 sites that this molecule or this ligand can attach itself to a metal ion. We have hexadentate ligand. The hexadentate ligands, an example is the ethylene diamine tetraacetic acid that I said before. And you see here, this is the acetate form, tetraacetate. So this is one acetate group. This is the second acetate group. This is the third, and that is the fourth one. So the tetraacetate group, and on it, you see the lone pairs of electron are on the acetate groups. So this lone pair of electron, there can be formation of a linkage to a metal atom. And apart from these 4 tetraacetate ions, we also have the 2 amine group. That's why it is diamine tetraacetate. So this makes 6 sites for binding to a metal ion. So when this happens, a chelate is always produced when a metal ion coordinates with a 2 or more donor groups of a single ligand to form a 5 or 6 membered heterocyclic ring. So whenever you have 2 or more donor groups of a single ligand forming 5 or 6 membered heterocyclic ring, you form a chelate. And when the ligand is a large organic molecule that has more than 2 or more complexing groups, like the EDTA, that ligand is referred to as a chelating agent, and you form a complex that is called a chelate. And the chelate effect occurs when multidentate ligand form strong 1-to-1 ratio complexes with many metal ions. And looking at this chelate, we said that it should form a 5 or 6 membered heterocyclic ring. And the most suitable ligands that will fall into this category are the tetradentate or the hexadentate ligands. And because they can form 1-to-1 complexes when the cations react with the ligands. And like every formation, there'll be a formation constant when the ligands form complexes with metal ions. And they do so in a stoichiometric ratio of 1-to-1. That is 1 molecule of the ligand and 1 mole of the metal ion, regardless of the charge of the ion, whether it is aluminum, which is 3+, or iron 2, iron 3, they will always form ratio 1-to-1 complexation when the formation of the complex is carried out. And there'll be an equilibrium formed for the reaction. So we can easily calculate the equilibrium constant for the formation, which is called the Kf, and is also called the stability constant, which is also called Ks or K stab. So, and that is the formation constant is the concentration of the product divided by the concentration of the reactant. So here we have our the reactant silver ion complexing with ammonia, which is a monodentate ligand, to form a silver ammonium complex. And the formation constant will be the product divided by the reactant, the concentration of the reactant, which is a silver ion and ammonia molecule. So the complexation reactions that can be used, not every complexation reaction can be used as a volumetric technique. It's not all the time that your metal ion complexes with the ligand that you form that you can be useful as a complexation reaction technique or complexometric titration. So there are some criteria that should be fulfilled. The first one is that reaction between the metal and the ligand should reach equilibrium rapidly. Whenever you add your titrant, which is your ligand or your complexing reagent to your metal ion, the reaction should reach equilibrium quickly. And also, the reactions in which interfering situations happen should not arise. That means that the formation of several different complexes of the metal ion with the titrant during the titration process, you don't want other metal ions that you are not interested in to form complex. Let's say you have a mixture of ions in a particular solution. You only want your target metal ion to form a complex. So other interfering situations or interfering complexes, you don't want them to interfere with the metal of interest that you want to titrate. And also for this reaction, for this complexation to be useful as a volumetric technique, there should be an indicator that will signify the end point or the equivalence point with fair accuracy. So you must be able to reach a portion whereby you can indicate that the reaction has been completed. So there should be a suitable indicator that will tell us when this has occurred. Then complexation titrations are also useful for the determination of large number of metal ions in solution. So, but in practice, EDTA, which is your ethylene diamine tetraacetic acid, as a titrant is a very popular and is the most common titrant that is used in complexometric titrations. So like I've shown you this before, the EDTA, the E is the ethylene, D the diamine, the T there the tetra, and the A acetic acid. And as shown before, you have 4 acetate groups, your 4 carboxyl or the 4 acetate groups. So when it becomes, there's a loss of the proton, this becomes an acetate ion, and that is the site of complexation with metal. And in addition to these 4 acetate groups, you also have the 2 amine groups, the diamine, with the lone pair on the nitrogen atoms as a binding site. And when we're writing the equation, because it's a very large, it's a macromolecule, we can simply refer to use H4Y as the annotation for EDTA. So, and due to the low solubility of acid form of EDTA in water, we normally use the disodium dihydrate EDTA salt. And you can see here now that the 2 ends of the 4 acetate ends, 2 of them have been replaced with sodium. So sometimes you see with the loss of water, so most of the time, the EDTA we use so that it can be soluble, we use the disodium form of the EDTA, and that's the structure Na2H2Y, 2 water. And that means that 2 of the hydrogen here have been replaced with water. But simply put, your EDTA is H4Y, but in the disodium, 2 of this hydrogen has been replaced with sodium. So we now have Na2H2Y and the water of crystallization that's there. So this is the soluble form of the EDTA that can be used for complexometric titration. So we said before that EDTA has 4 carboxyl groups and 2 amine groups. So we said that EDTA is a hexadentate or polydentate ligand that can donate 6 lone pairs of electrons to form a coordinate covalent bond with the metal. So irrespective of the metal here, there is a central atom. So this is the 1 bond from 1 acetate, the 2nd acetate, the 3rd acetate, the 4th acetate, and the 2 amine groups that donate the lone pair on the nitrogen. So this is a metal EDTA complex. You can say is, like we said before, that it's a 5 or 6 membered ring when you form a chelate. So the stability of this metal ligand complex, how stable are they, is influenced by a number of factors. And these factors relate to the nature of the ligand, as well as the nature of the metal ion. So let's start with the nature of the metal ion. Small ions that have high charges have stronger complexes. So on the periodic table, we have some ions that are small in ionic size, but they have high charges. Such metal ions will form strong complexes. And also the nature of the ligand. A multidentate ligand is expected to be more stable than the one that is formed by a monodentate ligand, e.g. ammonia. So the nature of the ligand would also lead to the stability of the metal ligand complex. Also, the basicity of the ligand. The greater the basicity of the ligand, the greater the stability of the complex. Remember that ligands are Lewis bases, and the stability of them will determine the stability of the complex. What are the other factors that enable the stability of the metal ligand complex? The size of the chelate ring. When you have four or five or six membered rings, it is more stable than when you have a linear chelate, or maybe two member or three membered. So the larger the number of the members of the ring that is formed, like the previous example we saw, the more stable that ligand, that complex will be. Then the number of the metal chelate rings. The stability of the complex is also directly related to the number of the chelate rings formed between the ligand and the metal ion. The greater the number of such rings, the greater the stability. And also steric effects. When there is no steric hindrance, such metal ligand complex is expected to be stable. So we said before that EDTA is hexaprotic because there'll be four acidic hydrogen, and two ammonium protons will be lost. And that is why it's H6Y2 plus. But the neutral acid is tetraprotic, which is designated by H4Y. And you know where the H4 comes from, the four acetic acid groups on the EDTA. So the proton from the carboxyl group, and each of these four protons that are replaceable, they have their different dissociation constants. So these are the four protons, and the first proton, when it is removed, you have its own dissociation constant. The second proton, the third proton, and the fourth proton. You can see the Ka values, the pKa values of the four protons that are successively or stepwise dissociated can be calculated. What are the advantages of EDTA being used as a titrant in complexometric titrations? EDTA will form stable complexes with various metal ions, and the complexation occurs in a single step. And hence, the titration of the metal produced a sharp change of the metal ion concentration at the equivalence point. All metal EDTA complexes are water soluble, so the study can be performed in an aqueous media. And like we said before, they form ratio 1:1 complex to all metal ions, irrespective of the charge. So let's say this is not manganese, this should be Mn plus. N here is the number of ions, and you have your EDTA and in an aqueous form. So you have your complex and you have the hydrozonium ion. That is an equation that can used to represent your metal ion complexation. But what are the limitations of using EDTA as a titrant? Sometimes there could be formation of insoluble hydroxides, and that is why EDTA titrations are usually carried out under alkaline pH. And to make this to be done, whereby your pH is not considerably changed, you make use of buffer solution. Remember, we talked about buffers when we're doing acid-base titration, that a buffer is a solution that will resist a change in pH. So we use buffer solutions whenever we are titrating with EDTA, because there could be some formation of insoluble hydroxides. And when these hydroxides are formed, they could compete with the complexation process. So the pH must be under strict control. Also, EDTA is not selective. What we mean by this is that because EDTA can complex with virtually all metals, if you have several metal ions in your aqueous solution, EDTA would form metal complexes with each and every one of them. So there is no selectivity if you have a mixture of metal ions, or if you just want metal ion that is the solution, there's no problem with that. EDTA will just target that and complex with it. But in a situation whereby you have other competing metal ions, EDTA will form complex with all of with most of them, and such complexes are usually stable. Now, the formation constant, we said that EDTA will form complexes in ratio 1:1 with every metal, almost all metals, irrespective of the charge of the metal ion. And the stoichiometry will be the same for all metal ions, like with the equation we said before. EDTA is Y4 minus, and this is Mn plus, that's the number of the charge on your metal. This is the 4 replaceable hydrogen on your EDTA, and will form MyN minus 4 plus. And that is the absolute formation constant of the complex. This is the your product divided by the reactant. So now, how do we know for every titration? It's not you can't continually run your titrant endlessly. You must get to a point where the reaction is said to have been completed. So how do we detect endpoints in complexometric titration? We use metal ion. There are 4 different types of methods. The use of metal ion indicator. Sorry, that should be indicator, not indicator. Indicator. Use of mercury electrode. The use of glass or pH electrode, and ion selective electrodes. So we can use electrodes to determine once there is a change in the pH or the electromotive force of the electrode that you used, you can say your reaction has come to an end. But for this course, we'll be placing emphasis on the use of metal ion indicator as the method of detecting endpoints of EDTA titration. So what are these metal ion indicators? These are compounds that will change whenever they bind to metal ion. And so for a metal ion indicator to be useful, it must bind less to the metal more than the EDTA does, meaning that at the start of the reaction, your metal ion is added, your indicator is added to your solution that contains metal ion, and it will bind, the indicator will bind to the metal ion. But at the end of the day, remember that it's your EDTA or your ligand that should bind to the metal. So it should bind, not that it's not going to be a very stable relationship, such that the strongly binding capacity of your EDTA will strip off the indicator when the ligand reacts with the metal ion. Examples of the EDT metal ion indicators, we have aerochrome black tea, calgamite, murexide, xanilol, pyridazanophenol. So these are the different examples of the metal ion indicators. So let's use an example of aerochrome black tea as an indicator. So you have your metal. In this case, we're using a magnesium metal. And you add, just like your every indicator, about 2 or 3 drops of your indicator. When it's added in the burette, so the metal ion solution, aerochrome black tea will be red. Assuming your solution is a clear solution, you now add aerochrome black tea, you have a red coloring. Your EDTA is colorless. So when your EDTA will be in your burette, your metal ion and your indicator will be in the conical flask. So by the time you start running your EDTA, at the end point, when the EDTA strips off this indicator to bind itself to the ion, and the indicator will now be taken away from the metal ion, the indicator color will change to blue. So once the color changes from red at the start, then you run your EDTA, and at the end point, the solution turns blue. So most metal ion indicators, they work like acid-base indicator. So if the metal ion indicator does not dissociate easily to release the metal to the EDTA, then the metal will be blocked. So you want to such that the metal ion will dissociate from the indicator, and the EDTA will react to the metal ion to form a metal EDTA complex. So the indicator is added, and so whenever the metal is blocked, that means that you cannot get the metal to react directly with the EDTA. We can use back titration, whereby you add excess of your EDTA and can be added in the titration of copper, and you now add copper as a second titrant. The excess EDTA will react to the copper, and you now work back and get the concentration of your magnesium ion. So EDTA metal ion indicators are also called metallochromic indicators. They are organic compounds that are capable of forming intensely colored complexes with EDTA. So they form intensely colored complexes, and the metal ion indicator complex is weaker than the EDTA complex, like I said before, and it has different color than the uncomplex indicator. So what this simply means that you first form a complex between your metal and the indicator at the start of the reaction. But this complex is not a stable complex, it's a weak one, such that when you start running your EDTA, the EDTA displaces the indicator from the metal indicator complex to now form your metal EDTA complex. And when this has been finally done, there'll be a color change, which shows that the uncomplex indicator has been stripped of the metal ion indicator complex. And during the course of the titration, the metal ion from the metal indicator complex will be replaced with the metal EDTA complex. So now, what are the requirements needed for metal ion indicator to be useful in complexometric titration? Number one is there must be a sufficiently color change. You want there should be a sharp contrast in the color at the initial start of the equation, the reaction, and at the end of the reaction. Like the one we saw before, the color changed from red to blue. So it's so easy to see that a reaction has been completed when there is a color change. And the secondly, the color contrast between the indicator and the metal indicator complex should be observable. So your indicator when it is alone, and when your indicator forms a complex with the metal, the color should be very, very distinct. Then the metal indicator complex should possess sufficient stability to ensure sharp color change. So meaning that it should not be a transient color that will disappear almost immediately when you add the indicator. It should be stable for a while, a sufficient stability. So I'll be able to note the color when the complex is formed with the indicator, but it should be less stable than the metal EDTA complex, so that when the EDTA replaces the indicator, the change in the color will be seen separately. So the change in the equilibrium from metal indicator complex to metal EDTA complex should be sharp and rapid. You don't want to be an endless titration. It should be within a short period of time, and it should be seen as soon as the color changes itself. Although also the color reaction of the indicator should be selective. So the indicator should know when you are different metals, some of them have different color changes depending on the metal they are complexing in the solution. And also the indicator must be very sensitive to metal ions, so that the color change occurs near the equivalence point. So as soon as an equivalent amount of the metal ion has reacted with the ligand that is complexing it, the indicator must be sensitive enough so the color should be changed as soon as that occurs. Then the indicator must be stable in the titration medium. It should also be stable on storage, so you don't have to be preparing it at each and every time you are required to carry out titration. And all these requirements should be fulfilled in the pH range. Remember, we said that for one of the disadvantages of EDTA is that it is a pH dependent, so that insoluble hydroxides are not formed in the solution. So the indicator you are going to use must be stable within must be able to work within the pH range at which your proposed titration is being carried out. And the last but not the least, your indicator should be commercially available in adequate purity And what we mean by this is that if your indicator has, let's say it has maybe metal ions in it as impurity, that could also complex with your titrant. So must be of sufficient purity. So what's the theory of this metal ion indicator? I'm going over it again for emphasis. So this is your metal, and you have added a few drops of your indicator, and this is your titrant, your EDTA. What we expect is that the EDTA will replace the indicator to now have metal EDTA complex, and your indicator will be separated. But this reaction would only take place if this complex is more stable than the metal indicator complex. If this is more stable, your EDTA will not be able to strip off the indicator from the metal ion that it has complex with. So the stability of the metal indicator complex is given by this, the dissociation of your indicator, your metal reacting with the indicator to form your metal indicator complex, and that is the equation of that reaction. So these are examples of metal ion indicators and their structure. You can see they're all organic solvents. You have calgamites, when the color, when it's complex with metal, is wine red. Ericum black tea is also wine red. Murexide has different colors. When it complexes with the cobalt, nickel, and copper is yellow. With calcium is red. So some of them are selected with metals that they call, the color changes depending on the metal they are complexing with. Xanilon orange is red, and pyrocatechol violet is blue. So we'll look at a few of them. Ericum black tea, this is a structure, is a sodium salt of 1-hydroxy-2-naphthalazole, 6-nitro-2-naphthanol, 4-sulfonic acid. Quite a very long name. So this is, you can see that is an organic reagent with a sodium salt of an organic reagent. It is a dark powder with a slightly metallic luster, and it is used to estimate the levels of many metals like the magnesium, zinc, manganese, cadmium, mercury, lead, copper, aluminum, iron, titanium, cobalt, nickel, and platinum metals. Then it is, how do we prepare it? Dissolve 0.2 gram of the Ericum black tea powder. It comes in the powdery form. You dissolve it in triethanolamine, another organic solvent, and you add 5 ml of absolute ethanol to it to form it. And you only need it in a drop-wise manner, 1 or 2 drops in your titration. The murexide also is used for EDTA titration of some metals like calcium, nickel, cobalt, zinc, cadmium, and copper. The murexide is usually dissolved in water, and because of this, it's not stable. It must be prepared freshly, unlike the ones that are prepared in organic solvents. Xanilon orange this is the structure, is also used to estimate the levels of bismuth, cadmium, lead, scandium, thorium, zinc metal ions using EDTA as a titrant. Then we have pyridilazonaphthol, simply called PAN, is used to estimate levels of cadmium, copper, indium, scandium, and zinc metal ions in back titration and EDTA replacement titrations. So we have different types of EDTA techniques, titration techniques. We can have direct titration, back titration, replacement or displacement or substitution titrations, alkalimetric titrations, and indirect titration. So we look at these different types of EDTA titrations one after the other. The direct titration is just like your acid-base titration, whereby your titrant is run from the burette into your conical flask that contains your analytes, and once there's a color change, that is the end of the reaction. So for metal ion reacting with EDTA, you just form the metal EDTA complex. But like I said, because the EDTA solution works at optimum pHs, so the metal ion will be buffered to the desired pH by using buffer solutions, and then titrated with the standard EDTA solution. So the essence of the buffer there is to keep it within the range of the pH whereby it's optimum for the EDTA to complex the metal ion. Some auxiliary complexing agents like ammonia, tartrates, and citrates can be used. So we said that the auxiliary complexing agents are the buffer solutions that will prevent the precipitation of the hydroxide of the metal ion. Remember, we said one of the limitations of EDTA titration is that soluble hydroxides can be formed of the metal ion. So to prevent this, we use buffer solutions of ammonia, tartrate, or citrate so that this would not take place. So some metals can be prepared and determined directly using direct titration, and the examples are copper, zinc, and nickel ions. Then remember we talked about back titration when we're talking about general introduction to titrimetry, that we do carry out back titration when there is no indicator or when the reaction is not fast. I gave you 4 different reasons why we make use of back titration. I expect you to go back to your notes on that to know why we use back titration. And one of the reasons is the use of this EDTA in EDTA titration. So in this case now, we use an excess amount of EDTA that is required to titrate the solution of the metal ion, which is your analyte of interest. And because we have used excess of the EDTA, you have, after the reaction is completed, your complex has been formed between the metal and the EDTA. The excess EDTA, which did not react with the metal, will now be back titrated with another metal ion within the presence of the indicator, and we now add another endpoint. So you can now do your calculation to get the quantity, the concentration of the ion that actually formed the complex with the EDTA. So the metal ion that is used in the back titration must not displace the analyzed metal ion from the EDTA. So let's say you have metal A forming a complex with EDTA. So you have metal A with EDTA. Then the excess EDTA is now titrated with metal B. And that metal B should not displace A, which is our analyte of interest, from the metal EDTA complex form. So examples are zinc chloride, zinc sulfate, magnesium chloride, magnesium sulfate that are used as standard metal ion solutions. Then we can now use these as the second ion that we use for back titration. Your aluminum ion, cobalt, lead, manganese, mercury, and nickel cannot be used, can be determined by the back titration method. The third type of EDTA titration is the replacement or displacement or substitution titration. And what happens in this type of titration is that your analyte is treated with an excess of your metal EDTA complex to displace the metal ion, and it is now later titrated with the standard EDTA. And what happens, why do we use this? Whenever the metal ions do not have satisfactory indicator. So in this case now, you have your metal ion, you don't have magnesium EDTA. You've already formed the complex between magnesium and EDTA. This is your metal of interest. So what happens is that this metal of interest will now replace or displace or substitute this magnesium ion to now form a complex of your metal ion of interest with the EDTA. So in this method, the weak EDTA complex of another metal ion, so this is your weak EDTA complex, is added to the solution of the metal ion of interest, which is your analyte. So magnesium EDTA and zinc EDTA are usually used as the weak one. Then your analyte of interest will replace it. You now have your metal ion complex. So the weaker metal EDTA complex is replaced with a strong metal EDTA complex. So this is the weak EDTA complex now being replaced with your analyte of interest to now give the strong metal EDTA complex. And the equivalent amount of the metal that is freed from the weaker complex cannot be titrated with a standard EDTA solution. So whatever is freed from here cannot be titrated with an EDTA, and you can now determine your metal ion in the concentration. And this method is useful for the determination of calcium ion. Then we have alkalimetric titration, another type of EDTA titration, whereby in this case, it operates using the principle of liberation of free hydrogen ions during complexation. So an example is the reaction between a metal ion and your EDTA to produce your hydrogen ion, free hydrogen ion. So this free hydrogen ion that is now titrated, remember that it is acidic, can now be titrated with a standard solution of a base, like so a strong base like sodium hydroxide, using a suitable acid-base indicator. And this now, whatever concentration you get from here, you can use that to extrapolate the concentration of your metal ion indicator. Then we have the indirect titration. And this method of EDTA titration is used to determine the ions such as halides, phosphates, and sulfates. And these ions do not form complex with EDTA. Remember that what is forming complex with your EDTA is your metal. But if you have a solution of maybe your metal halide or your metal phosphate or your metal sulfate, you can find the concentration of your anion from the titration. So an example is the determination of sulfate ions in the barium sulfate solution. Remember that the barium ion there, which is a metal, will form a complex with your EDTA, and there'll be a precipitate of barium sulfate, which can be filtered off, and the unreacted barium ion will be titrated with the EDTA. So you can now get the concentration of your sulfate ion can be indirectly determined. So anions that form precipitate with certain metal ions can be analyzed with EDTA by indirect titration. So example that I've said before is the sulfate ion. It precipitates with excess barium ion at a very, very, very low pH. So when this happens, the barium sulfate will form a precipitate, will be filtered and be washed, and the excess EDTA will be added, and then the pH is increased to 10, and your barium ions in solution will be formed with the EDTA, and the excess EDTA is now titrated with your magnesium ion. So how do we increase the selectivity of EDTA? Since we said that EDTA is not selective, it can bind with almost all the metals in the solution and form complex. How do we increase the method of selectivity? We can use the chemical separation, the control of pH, the use of masking and demasking agents, as well as kinetic masking. So we take them one after the other. Chemical separation. In this particular technique, the selectivity of EDTA is increased by separating the species from other components from the sample solution. So other species that are present that would interfere with EDTA or compete for EDTA complexation will be separated. So the separated species is then dissolved in suitable solvents and titrated against EDTA using a suitable indicator. And an example is calcium ion, magnesium, nickel, and copper ions can be first separated as calcium oxalate, nickel dimethyl glyoxinate, magnesium and ammonium phosphate, and copper thiocyanide. So these ones can be separated in this form, and the precipitates that are formed are now dissolved in suitable solvents, which can now be titrated against EDTA using an indicator. So you first of all form a precipitate of either an oxalate or dioxinate or ammonium phosphate. Then the precipitate is dissolved and later on titrated against EDTA using it as using an indicator. Then we have the pH control. In this case, the selectivity can be increased by controlling the pH of the solution. That is, the hydrogen ion concentration will be controlled. So by adjusting the pH of the sample solution, it's possible to allow a single species to react with EDTA. So sometimes if you have a mixture of ions, some ions will be more selective at certain pHs. In water, for example, where you have calcium and magnesium ions, calcium and magnesium can be titrated in strongly alkaline solution, whereby some other ions that are trivalent, like bismuth and iron, can be selectively determined in a very strongly acidic solution at about pH of 2. So by varying the pH, different anions can form, different cations can form complex with EDTA. Then we can also make EDTA to be more selective by the use of masking agents. The masking agent is used to prevent the elements from interfering in the analysis of another element. So it's used to prevent the elements from interfering in the analysis of another element. Let's say you have other elements that will be competing for the EDTA complexation. If you use a masking agent, the elements will not interfere with the other one. Masked elements can be demasked after the analysis so that your analyte of interest can react with the one that has a stronger affinity for when the titration is completed. So masking agents act either by precipitation or by formation of complexes that are more stable than the interfering ion EDTA complex. So you can mask by precipitation, or you mask by the formation of complexes. So the process of which a substance is prevented to take part in the reaction without physically separating it, like the one we said before, is called a masking process, and what is used as the masking agent. So you can mask by precipitation, and this is common with some heavy metals like cobalt, copper, and lead. So they form insoluble sulfides using sodium sulfide, or they form insoluble complexes using thiacetamide. So, and when the complex is formed by precipitation, they are filtered, decomposed, and then titrated with disodium EDTA. We have other common precipitating agents. We can use sulfates for lead and barium, oxalates for calcium and lead, fluoride for calcium, magnesium, and lead, ferrocyanide for zinc and copper, 8-hydroxyphenolane for many heavy metals. So we also use glycerol as a masking agent to mask copper by precipitation in the acid of solutions that contain copper and zinc. Then potassium cyanide reacts with silver, copper, mercury, iron, zinc, cadmium, copper, nickel to form complexes in alkaline solution. Potassium iodide is used to mask the mercury 2 ions as mercury iodate and is specific for mercury. It can also be used in the assay of mercury 2 fluoride. So iron also form highly colored complexes, triethylamine. Also different types of complexes can be formed depending on the precipitate you want to generate and the metal ion involved in it. So demasking is just the opposite of masking. After you have masked, then the remaining free cation is titrated with the EDTA. Then the previously masked cation can be demasked using a suitable reagent to get the free cation. Now the free cation is now demasked, titrated using standard EDTA. So the determination of cadmium or zinc, when you initially form a complex of cadmium cyanide, you can use formaldehyde, chloral hydrate, or methanol acetic acid to demask cyanide complexes of zinc and cadmium. So here you can see formaldehyde. This is the complex of zinc and cyanide, and you have formaldehyde. It gives us this. Then the free zinc ion is then titrated using standard EDTA. So this is not titrated with EDTA, and you cannot determine the zinc in the presence of calcium. So kinetic masking would be undergone by some metals that undergo fast completion, and we have some metals that undergo slow completion with EDTA. So we can selectively work on their rate of reaction and titrate the metal ions that have fast completion with EDTA, while those with the slow metal ion, complexation rates will now be titrated later. In the presence of chromium, ion 3 can be titrated together with chromium 3 because chromium 3 reacts only with EDTA, as compared to iron 3. So you first titrate with iron 3 and later on titrate with your second metal ion. So you can make use of kinetics to selectively use our ADTA to transfer our uh, to titrate our metal ion with EDTA. So what are the applications of complexometric titration? They have been used in the determination of a lot of metals in different formulations, in environmental samples, in water, in food, stuff, and the likes. We also use it to determine the hardness of water. We know that water hardness is caused by the presence of calcium and magnesium ions. So, and these are metals that can form complex with EDTA, and we can use that to determine them. So an example of that, like I said before, is water hardness. So water hardness is as a result of the concentration of multivalent metallic cations in water, which determine the capacity of the water to precipitate soap. So depending on the anion which it associates, hardness is classified as calcium and magnesium hardness, carbonate hardness, and non-carbonate hardness, and pseudo hardness. So we've all done this before about hardness. They have temporary and permanent hardness. The temporary hardness is due to presence of bicarbonate of calcium and magnesium, is sensitive to heat and precipitates readily at high temperatures. While permanent hardness is due to the presence of chlorides and sulfates of calcium and magnesium, and you cannot remove this by high temperature. So water hardness, we have said that is mainly due to the presence of calcium and magnesium, but we have other ions that can cause hardness, like iron 2, iron 3, strontium, and aluminum, which are in relatively low quantity. Then calcium and magnesium ion, they enter water supply by leaching from minerals within an aquifer. So the common calcium containing minerals are calcite, calcium carbonate, gypsum, and dolomites, which is calcium and magnesium carbonate together. So how do we determine hardness in water? We can determine hardness by titration with EDTA using Ericum black tea as an indicator. The indicator reacts with the metal ion to form a complex that is red in color. Then the EDTA would displace the Ericum black tea in the complex, and when the replacement is complete, the solution changes from red to blue. So we have an example whereby 0.01 molar EDTA is titrated with calcium to determine the hardness of calcium carbonate, and usually it is required as reported as milligram of hardness of carbon carbonate. So this is the procedural chart. You have your water sample, so you can prepare it up to 22 ml of your sample. Then you add your ammonia buffer. Remember, I said we must put buffer there because we want to control the pH. Then you have 2 drops of Ericum black tea. Then you now fill your burette with this tea. You now turn the tap to titrate, and at the end point, you see that there's a color change, and you calculate the total hardness from there. So this is an example and an experiment to determine the amount of hardness in the water sample. 20 ml of the water sample was added to 2 ml of ammonia buffer and 2 drops of Ericum black tea indicator. The color of the water sample turned red. This was titrated against the EDTA filled in the burette. The tension was continued until the solution turned blue. The experiment was carried out 2 times to get 3 concomitant results. Calculate the total hardness of water in the sample. So just like every other acid-base titration, you have your titer value, your burette, you take your sample that contains your metal, about 20 ml in this case, and you fill your burette, and where there's a color change, you note your final burette reading, and you get the volume of EDTA used. And from the volume of EDTA, you can calculate your average titer value. And in calculating hardness as milligram per liter carbonate, is the volume of EDTA multiplied by molarity of EDTA multiplied by 100,000 and divided by the volume of sample taken in ml. The reason why we have multiplied by 100,000 is that molecular weight of calcium carbonate is 100 grams. but we need it in milligram per liter. So it's going to be 2960 milligram per liter. So now the EDTA titration curve, just like we have titration curve for acid-base titration, we also have titration curve for EDTA. And you can use, in the course of the titration, we can get a curve for the EDTA titration, and it is similar to that of the acid, strong acid and weak base titration, and it follows this order. So you see now that this is, you have your, at the beginning of the titration, you have just your EDTA, and you have more of the metal ion. Then you have the sharp rising steepy curve, and at the end point, you have more of your EDTA that has reacted. And if the KF is large, the reaction is considered to be complete at each point of titration. So like I said, we have three regions before the equivalence point, as you can see here, at the equivalence point and the post-equivalence point. So before equivalence point, the addition of EDTA is consumed completely at this stage. As you're adding it, the metal ion is complex with the EDTA, so we have excess of metal ion at before equivalence point. And the concentration of the free metal ion is equal to the concentration of the excess unreacted metal ion. So the dissociation of metal ion indicator is negligible. At the equivalence point, the concentration of the EDTA is exactly at that of the metal ion in solution. Solution is treated by if it is as if it is dissolving pure EDTA. The post-equivalence point, the entire metal ion has been virtually consumed, and all you have is your EDTA. So in case of metal EDTA titration, the EDTA is added to the buffer solution of metal, and you can calculate the negative logarithm of the metal ion indicator during the titration. So you plot a graph whereby your PM is on the y-axis, and your EDTA, volume of the EDTA, is on x-axis. As you can see here, this is the P of M, and this is your EDTA. The curve is given the point of inflection at the equivalence point. The curve of PM against volume of EDTA added is known as the titration curve of metal in the EDTA titrations. So this is the transition curve. So an example is given as follows of a typical titration curve of calcium with EDTA. We're given the absolute formation constant KMY for calcium ion and EDTA complex with 5.0 times 10^10, and alpha 4 at pH of 10 is 0.05. K prime My equals to KMY plus alpha 4 equals to 5.0 times 10^10 times 0.35 equals to 1.8. So now what we simply did was to substitute this your formation constant and multiplied by the alpha 4 of the formation constant. So now the solution is that to do this, to take 10 cm cubed of this molarity of calcium ion buffered at pH of 10, and you titrate with this after the buffer solution has been made. Now, when you do this titration, you have to calculate the pCa of your metal at the start of the titration after adding 1 ml of titrants at the equivalence point and at the post-equivalence point. At the start of the titration, when no titrant EDTA is added to the solution, it's only calcium ion you have at the start. So before you start adding your EDTA, the only concentration there is your calcium ion. And we're told that the calcium ion has a molarity of 0.01. So if calcium ion concentration is 0.01, the pCa is minus log 10 into Ca plus minus log 10, and you substitute into the concentration to give 2.0 to give pCa minus 10. Sorry, I'll take that again. When you start your titration, the EDTA is added to the solution, and only calcium carbonate is present because we've not added the calcium ion solution. You've not added your EDTA. So when you start, before you run your EDTA, only calcium ion is present. Then later on, at that particular point in time, you have just the molarity of your calcium, which is 0.01. So you can find your PCA, which is the negative log of the molarity of your calcium ion, which is going to be 2.0. Negative log of 0.01 will be 2.0. Then the next one is the addition of 1.0 cm cube of the potency, which you find at the start of the titration. After you add 1 cm cubed, then of the titrant, the equivalence point, and after you add 11 cm cubed of the titrant. So we are moving to the next one. We add 1 mil of the titrant. When you add 1 mil of the titrant, it's not yet the end point, the equivalence point. So what we'll have is that you have a partial, it's a certain amount of EDTA had reacted with calcium ion. So since the titration is the ratio 1:1, so you expect by that time that only 1 mil of calcium ion would have reacted with 1 mil of EDTA and to form that complex. So you have 9 cm cubed of the calcium ion that has not reacted. So to find the PCA, we now multiply. That means that the total solution now is 11 mil. You have 10 mil of your calcium ion solution with 1 mil of EDTA, that will be 11. And this is the molarity, and this is the volume of your calcium ion multiplied by the molarity divided by the total volume will give you the molarity of the PCA. So minus PCA will now be the negative log of the calcium ion concentration, and that will be minus log 10 of this to give your PCA of 2.09. Now, at the equivalence point, we expect that your 10 mil of titrant will react with 10 mil of the calcium ion, and it will form a complex, and the total volume of the solution will be 20 cm cubed. So you have 10 mil of your calcium all reacted. This is the molarity of your calcium ion, and this is total volume. So that will be 0.005 molar. So an at equivalence point, the equation of the calcium ion will be equal to the concentration of the EDTA. So the equation of the EDTA is this. You see, your calcium ion is equivalent to the concentration of the EDTA since they are at equivalence points. So at that particular point, so your dissociation constant is your calcium EDTA complex divided by the calcium ion concentration and your EDTA concentration. But since we said that at the equivalence point, your calcium ion concentration is equivalent to the EDTA concentration, so this can be equal to your calcium ion concentration. And your KMY was given as 1.08 times 10 to the minus 10. So you substitute that. You also now your calcium ion concentration, as we've said before, is 0.05 mol, which is the same for the two of them. So you can now, this is your 0.05 mol. You know this, and you now find your calcium ion concentration. And that will now be, find the square root, substitute that, find it to be 5.2 times 10 to the minus 7. So P of Ca of your ion now be the negative log of this, so now give 6.28. Then after the addition of the EDTA, 11 cm of EDTA, that means you have 1 mil of calcium ion that has not, and 1 mil of EDTA excess that has not reacted with the calcium ion, and that means that your calcium ion solution is still 10 mil of it. This is your molarity. You now have 21 mil. By the time you add 11 mil to 10 mil of the complex, the total volume will be 21. And you can get the molarity. So now the excess EDTA will now be, this is the molarity of the excess EDTA. And the concentration of the EDTA is given by CY. So your CY now of your EDTA is 4.76 times 10 to the minus 4 M. We are not interested in that. We're interested in the concentration of your calcium ion. So what we do is substitute for this, which is your CaY2 minus, which you have gotten here. Your calcium ion concentration, we've done that before, which is, we are looking for calcium ion concentration. Your CY is 4.76 times 10 to the minus 4, which we obtained here before. and you substitute that into the equation, you can get your CA, and your minus log of CA is going to be PCA. And this is an example of a titration curve of 0.01 molar EDTA and your PCA on your y-axis. So as you're getting different values of this CA, as you're adding the different volume, remember that at the time we added 10 mils of EDT, that is this point, these are equivalence points. And beyond that, this is your post equivalence point, and this is your pre equivalence point before we add equivalent volume of EDT. Thank you very much. So if you have any question on that, on complementary titration, feel free to ask on the via Zoom. I'm looking at one of these days that we have a synchronous class whereby we'll be asking questions as the lecture goes on. Thank you and have a nice day.